Hello everyone. So let us start our discussion with mathematical model of synchronous machine. Here one thing you must keep it in your mind that henceforth we will do most of the derivation for salient pole synchronous machine. However, later on you can always remove that saliency and easily have a simplified model for cylindrical rotor machine. This is a cross-sectional view. You know that system that is having projected pole is salient pole rotor, and this is one is having round rotor. Although here four poles are shown, but in our discussion most of the times I would like to keep it like a two pole thing because that will simplify our overall discussion. And here see, let us proceed. This is very important circuit model for an ideal machine. One thing I would like to say here that like previous case also here instantaneous values we are considering. This small letter indicates instantaneous value, and these are the physical position of our machine. And here one more thing I would like to mention that we are considering motoring mode. Later on we can also consider the generating mode of that machine, and we will not have much difficulty in doing so. Now here this IA, IB, IC, here you can see that they are means inflow indicates that your machine is operating in motoring mode. Now stator part is known to you. Now come to the rotor part. Here you will see a few new elements, but not totally new to you. If you see that here this if it indicates the field winding, the magnetomotive act means magnetic field produced by the field winding will obviously along d axis, and means if you want to see the physical position of the field winding, that means physical field winding is supposed to be wound in this way, right? And there is another winding kd, that is the damper winding attached with our field winding. Now if you have a question on damper winding, I would like to request you to check your Netris account, and you will see that I have already sent a few PDF files on damper winding. But for a short review on damper winding, like as we know synchronous machine is not self-starting. Why it is not self-starting? Because like I hope you have read that uh, PMMC instrument, permanent magnet moving coil instrument. Now what happened in case of PMMC instrument, when you feed it with an AC, suppose you with a PMMC DC voltmeter, if you try to measure it an AC voltage, you will see that your pointer is exhibiting or means oscillating motion, means and if you increase the frequency of your supply, the amount of oscillation will be getting down. Now that the interesting phenomena is that the average torque becomes zero. So kind of similar things happen in case of synchronous machine. As we know that synchronous machine operates in principle of magnetic interlocking. So if your supply frequency, suppose it is 50 Hz, and say like 4 pole 50 Hz structure, you are going to get a 1500 rpm rotating stator mmf, rotating mmf. Now if you do not means allow your rotor to reach a subsynchronous speed where the relative speed difference between your rotor and stator is very small, rotor will not be able to align itself with the stator, means so that is why the synchronous machine is not self-starting. And in order to make it self-starting there are many methods, but let us means discuss only damper winding method. What is the damper winding? A damper winding is like a squirrel cage uh, induction motor rotor conductor structure that we take from squirrel cage induction motor, means the same structure is placed on our induction machine. Sometimes it is placed on that, in case of salient pole machine we placed it uh, near the pole face. So means pole base, actually not face, pole base. So what happened, and these damper windings are like squirrel cage induction motor rotor circuit winding, they are also short circuited. So what happen when you means your you feed your induction machine, sorry, synchronous machine stator with a three-phase balanced supply, it produces a rotating magnetic field, and this shorted winding on your synchronous machine rotor, known as damper winding or amortizer winding, they produced a torque by virtue of induction motor, means induction the motor a similar action like induction motor, and that helps your machine to reach a speed, as we know that in case of induction motor, squirrel cage induction motor, our no load slip is very very small, so it helps our synchronous machine rotor to reach a value that is very close to its synchronous speed, and then the rotor, the magnetic pole on your, you energize, you provide means connect this VF with your rotor winding, and it produces a magnetic field, and then the rotor accelerates itself and lock it by means of magnetic interlock. So this is KD, and obviously as I have already mentioned, it is short circuited. Similar winding, this KQ is like this G and KQ may be present, may not be present. In most of the cases you will not find them. G is like a means winding. Suppose if you have a means, this is the most generalized analysis we are trying to do here, so that it won't create much problem later, right? These are perpendicular and they are the means virtual thing. Now see here, this one, this G, it is KQ is like a damper winding that is placed on our quadrature axis, right? In most of the cases, in most of the machines, you will not find G and KQ, and even if you find KQ, you will never find G in machines, right? But it is present there just to for very very remote chances there, in case of some specially designed machine where you will be able to see the presence of this G winding, and that is why here we are incorporating this G winding also in our analysis, right? Now see, these are the MMF component along DQ axis. This is you are already known. This theta r, here we are considering that this rotating reference frame is rotating at a speed of rotor, means it is attached to rotor, right? So basically our transformation matrix will be KRS, means that Ks with raised index R, that indicates it will transform everything to our rotating reference frame that is attached to our rotor. Now in order to save some of our time, and here you will see lots of equation you will be facing, and in order to save our time, I just write them in a copy and just take a picture. So the A phase MMF produces two flux component along D and Q axis. So here this phi D and phi Q, they are the two phase means flux component along direct axis and quadrature axis. This PD indicates permeance along D axis, and this PQ indicates permeance along Q axis. So if you see by virtue of this structure, this FA, the MMF produced by our A phase winding, it will have a cosine component along. FAQ will be a cosine of cos theta, and FAD will be sine of theta angle. At a particular instant, I am again mentioning this term that we are dealing with instantaneous value. This PD and PQ, they are the two different value of permeance, means PD is permeance along direct axis and PQ is permeance along your quadrature axis. And if we see here, PD is along this direct axis and PQ is along this quadrature axis. So you can easily understand that any intermediate position. So here you can see that the cross-sectional view here is from cross-sectional view it is evident that PD is the permeance along direct axis and PQ is the permeance along Q axis, and obviously in this case we will get only one even permeance, not PD not PQ, a constant P will be getting here. So now as you are having this PD along direct axis and PQ along Q axis for salient pole rotor, you can easily understand that in case of any intermediate position, like if I suppose want to take here the permeance value, it will be an average of these two extreme cases, right? So phase flux linkage we can write like as we know that flux linkage can be found out by multiplying the number of turn. Here ns indicates number of stator winding turn and we are considering balanced three phase winding. So all the three phases are having ns number of turns. So this when we are multiplying the total flux with number of turns, we are going to get the flux linkage. Here you will see that this NSFA PD sin square theta r plus PQ cos square theta r, these two things are means when we put these two value here we are getting this equation, and eventually we are getting this the PD plus PQ by 2. Now here one thing will be you will readily understand that in case of our cylindrical rotor machine, as I have already mentioned, that PD is equal to PQ. So what you will be getting here, the two permeance will be same because there are no such means unevenness of you can observe in cylindrical rotor machine air gap. So therefore this term will become 0 and you will have a constant term, and that is exactly the case. And also you will have a constant flux linkage that happens in case of cylindrical rotor means cylindrical rotor synchronous machine or cylindrical rotor induction machine, right? Now if you see another means interesting thing here, that this is actually the second term that is due to means that is responsible for the saliency part means or explicit due to saliency, because this part is not explicit due to saliency. Even in case of a cylindrical rotor machine you can have this part, but this part that is due to saliency, that is the difference of permeance between direct axis permeance and quadrature axis permeance, it is varying twice with the cosine of twice of your rotor angle theta r, and that is how, if you can recall, I have already mentioned that we are considering a two pole structure, because four pole structure you will have a difficulty in visualizing the whole thing, but here this theta r is our means the twice the angle. So if that is the case, then what we will be getting here, the whole thing can be written as a constant A and another constant B, because your PD and PQ, these two are constant. For a given machine, your permeance along direct axis is a constant number, permeance along quadrature axis is also a constant number. So when you average them, you will be getting A, and when you find out their difference and divide it by 2, then also you are going to get another constant, that is B. So here now lambda BA can be found out in a similar manner. Only difference we need to create in case of lambda B, that BA, that is flux linkage between B phase due to A phase current. Here we are considering A phase flux linkage due to A phase current. So everywhere we have to consider this term, this phi d sin theta r, it should be replaced by sin theta r minus 2 pi by 3, and here also it should be replaced by cos theta r minus 2 pi by 3. So here we can see that sine theta are minus 2 pi by 3 and cos theta are minus 2 pi by 3. And another interesting thing here, you will see that we are getting lambda ba is equal to minus a by 2 minus b cos 2 theta r minus pi by 3, right? So you may ask me, sir, why this is only minus pi by 3? Why not 2 pi by 3? See, the thing is that this 2 pi by 3, this second 2 pi by 3, it depends on the stator winding position. It has nothing to do with your rotor mechanical position. Rotor mechanical position is only responsible for varying this part, because your this permeance, this is exactly varying with your rotor mechanical part, and that is exactly varying at a means twice means cosine varying proportional with cosine of twice your rotor angle. So it present everywhere, like in case of a normal machine, if you can recall, we usually get that here we usually get ls plus m, and here we will get means lss plus lms for a phase, and here we used to get minus lms by 2, but here you can see that we are getting minus a by 2 and minus b, this kind of things we are getting here. Now means if we proceed, what we will see that a phase LLA, now let us write as this means winding inductance, we can write LAA is equal to L naught. Okay. Now how to find out flux linkage and inductor? That flux linkage lambda is equal to L into I. Lambda means flux linkage is equal to the value of inductance into current flowing through that coil. So here we are assuming this is L naught is the constant, means if you divide this A by the corresponding current value, you are going to get L naught. Then this LAB is equal to LBA, because this AB, I will come to this BA part later, sorry, AB part later. BA part is due to your A phase current mutual inductance on B phase, and that is so you are going to divide this minus A by 2 by the same A phase current. That is how you are going to get here minus L0 by 2, and this remains same minus LMS. One more thing, here we are assuming that the machine is symmetrical. Now you may ask me another question, that why LAB is equal to LBA, because it is not a case of cylindrical rotor machine, it is a salient pole machine. But remember, this cylindrical and salient pole, this position depends due to rotor position, but rotor position is also means your windings are symmetrically placed with respect to your space, means spatial placement of your windings are symmetrical. It has nothing to do with your rotor position, and that is how we are getting AB is equal to BA, and also LAC is equal to CA, and accordingly we are getting the remaining term, right? So this is very interesting observation, that even we are having our saliency in rotor structure, still our mutual inductance are equal. Later on, if we go to more precise and in-depth analysis, we can see that they are not exactly equal, rather there is a small difference we can observe due to some other factors, but that is not under the purview of this present course and will complicate the whole discussion. So today here we can see that the this Vs indicates all the stator vector and means stator variables, voltage vector of stator, and Vr indicates voltage vector of rotor. Here we are assuming one thing, that the winding resistance, here it is Rs, and here there is a small correction I would like to suggest, that instead of RS here it should be RR, where RR is like a diagonal matrix, right? You can see the entries of RR, and this is, it is also a means vector of IA, IB, IC, that means stator current, while IR is having IR, IB, IC, IQ, IF, uh, all these currents this one is having, and these are the corresponding flux linkage of stator and rotor. Do remember this P indicates not the number of pole, rather it indicates the differentiation with respect to time. It is not very convenient for us to all the time write it like d by dt. So in order to means make it convenient, we have written it in this way. Okay, now here RS is armature or stator winding resistance, RF is D-axis or field winding resistance, RG is Q-axis field winding resistance, RKQ is Q-axis damper winding resistance, and RKD, it is the damper winding means D-axis damper winding resistance. I forgot to write this RKD, it is D-axis damper winding resistance. LS is armature or stator winding leakage inductance. LF is D-axis field winding leakage inductance. LLG is Q-axis field winding leakage inductance. I hope you can still recall the placement of F field and G winding. And this LKD is D-axis damper winding leakage inductance, and LKQ is Q-axis damper winding leakage inductance, right? Accordingly, LMD, that is LMQ, LMF, LMG, they are corresponding D-axis, Q-axis means magnetizing inductance, and LMF and LMG are D-axis and Q-axis field winding magnetizing inductance corresponding to D and Q axis. LMKD, LMKQ, they are D-axis damper winding magnetizing inductance and Q winding damper winding magnetizing inductance. So please note down all these means symbols, or means the way we are trying to indicate a parameter for a particular winding, because later on we need this. So this is our expression for flux linkage. Here you can see that this is lambda s is equal to LSSIS plus LSRIR, that is in Weber turn. Now here also this LSR, we are assuming this LSR to be a means matrix, and it is quite obvious that while you are trying to find out flux linkage of stator winding due to rotor current, you have to use LSR, while you are trying to find out the reverse one, that means the flux linkage of rotor winding due to stator current, you have to just obtain the transpose of that matrix. Now here this LSS contains all these terms. Here again you can ask me the question that why LSS, and I would like to help you to recall the fact that although the stator winding, that is means like a smooth cylinder inner periphery, but inside that means hollow cylinder you are moving an iron structure, and that cause an means uneven air gap, uneven time varying air gap inside your machine, and that is how you are getting different value of this self inductance LSSS. Now we will also investigate the element of LSR and LRR. So here one thing, can you answer me that why this LRR, it is independent of rotor position? LSS is dependent on rotor position, but LRR, that is rotor self inductance, it is independent of means rotor mechanical angle, while stator self inductance matrix, that is dependent on rotor angle, but rotor self inductance matrix is not dependent on rotor inductance, right? And obviously this one that is responsible for mutual coupling. Here another thing it is means we should note, it is almost like the normal case, only thing that previously we used to consider means the number of these number of columns LSR, this matrix, the number of columns depend on the number of variables or number of windings you are having on your field or rotor. Now here again you can see that these are means kind of means independent of our, means it is not varying with 2 theta, rather it is varying with just theta. So you should also try to think that why it is only LSR is varying with theta, not with 2 theta, right? So this is our transformation matrix, like CR we can write if we want to convert the all the quantity to our rotor side, we can write like this. We are familiar with this case R, and this I is a 4 cross 4 identity matrix, and this CR is totally a 7 cross 7 matrix. That means you have 7 different flux linkage, 3 due to stator, 3 different field winding, and 4 due to rotor, 4 different field winding. There are also 7 different currents, 3 due to stator current and 4 due to rotor different winding currents. So that is how you are getting this variable, and this 0 indicates null matrix where all the entries are 0. This is R3 cross 4, right? Now we'll see the voltage equation, right? Now here one thing you can see that this VQD0, right, it is the, here we are considering a matrix, this Ks raised index R, it indicates now we are trying to transform all these because our L matrix is if we consider LSS and other matrix, there are a lot of theta terms are there. I would like to explain it once again to you, that here this matrix is has lot of theta. Now if we go back to here you can see that we need to obtain the differentiation of lambda s. So lambda s, now if you look at the expression of lambda s is LSS IS. So if you try to apply differentiation or to try to perform differentiation of lambda s, then actually you have to perform DDT of LSS IS plus IS DDT LSS and likewise. So this, while you will try to perform DDT of LSS, as LSS is not a constant matrix, all these terms will give you a lot of means speed dependent term, means I will get something like d theta dt, and that will means you have to consider a lot of numerical variables, and it will make your model unstable. Actually, what is the essence of learning all this theory, this reference frame theory, and also whatever we are studying here, so our main objective is very simple. Our main objective is to, prior to, suppose you are means you want to apply or you want to design a synchronous machine. Now before you design, you must if it is not feasible, or means even if it is feasible, not always very economical to design a machine that is suppose you need to design a huge machine that can supply say 100 megawatt large turbo means synchronous alternator. Now or 100 means say 1000 horsepower or kilowatts power DODA means synchronous motor. So all these huge machines are not very easy to design, and even if you design, you are not supposed to risk their means health, means just to test their performance. You should not start that machine directly, or means rather how this machine is going to behave. If we can simulate in our computer environment, like what is simulation, let me give you a very simple idea. Like if I ask you that simulate a circuit that is having a inductor of 10 Henry and series RL circuit and resistance of 1 ohm. So instead of means bring a 10 Henry huge inductor and 1 ohm resistance, what you can do, you can just means take help of any simulation software like MATLAB or like our PSpice, PSCAD. We are having lots of simulation software, and using those simulation software you can simulate. You can see that if we connect these two physical element in series and if we apply a certain voltage, then how this circuit is going to behave with that voltage, what will be the magnitude of current, and how that magnitude of current or that current is going to vary with your time. So all these things are part of simulation. Similarly, here our main objective is that prior to this reference frame theory or all these discovery, people used to analyze all these things, and those analysis was only valid for steady state and also based on lots of assumption. But gradually people want to develop a more realistic model and more realistic model for their simulation. So even without having such a large machine, we can accurately, or means with means very close accuracy, we can predict how this machine is going to behave. So here now if we want to simulate, then obviously we need all these mathematical equation. But while you are trying to simulate this mathematical equation, if you have to take care of a huge number of data, means that are literally huge, means at every instance you can understand that if you increase the number of variables, then that is going to occupy more and more of your memory space. Like you have learned digital electronics, and you can understand that means how to design register counter. So it is not an easy task to solve a differential equation, and if that differential equation involves a lot of terms, so it also affects your stability of your numerical model. Numerical stability is also very important, that even if you design a model, there was a very popular term during our means when I was at means with a very primitive machine, say into 4th generation machine used to get hanged very easily. Means whenever we try to run some more complicated program that is very intensive to computer resources like RAM and other things, it used to occupy a huge number of memory space. Now with the advent of our solid state technology, all these things are now it's not present, or Rather, you are quite blessed that you have a very fast computer with a huge amount of computational resources, but that doesn't give you a blanket permission that you can waste it as you want. According to your own free will, you cannot waste them. So that is why it is desirable that you, before simulation, you apply some mathematical tools, some techniques, so that your total model will become a simplified one, right? So here what you will be having, this vqd, iqd, lambda q d0, all these are means we are transforming stator variable to a rotating reference frame that I have shown in my third slide, where the speed of that rotating reference frame is omega r. That means that rotating reference frame is locked with our rotor. And let us see that how transforming our variable to that rotating reference frame can help us. Right. So here, this is our KSR. Now, a few days back, one of the student asked me to show this derivation, and I think I have already show this derivation to him, that how this PQ is lambda D0, uh, this one we can obtain from this stator quantity VABC, how we can obtain a QD0 model, right? So with this here, you can see that the RS is very simple. It was a diagonal matrix. So whatever transformation you apply on your RS, means if you post multiply and pre multiply RS with a matrix and its inverse, you are bound to get RS once again, right? Now here, this one was a bit problematic to us, and I have already shared means derivation. Probably Chetan asked me one question and I have shared this derivation. So if you follow that derivation, you can get this one easily, right? Now here we can see that our this term, we are aware of this term. Now see that derivation, this is what, if we obtain the derivative of KRS inverse, we know that it will result omega r is the rotor speed. Do remember, this rotor speed is in electrical speed, it is not the mechanical speed. So we know that after performing we will get here this omega, all this derivation I have already shown. So combining our from VABC to VQD0, what we are getting here, that is RS, the diagonal matrix. So it is okay that we can write it RS over here, and then you can see this one, this omega r is like uh, this one. It is like this means, see that omega r, it is having its contribution, means the term, if we define this middle term as PDMA, because this depends on omega r. If you make omega r 0, then you will not be able to get any such speed EMF in your picture. Now this omega r, see the beauty of this equation here, you will see that the last row of this matrix that I have marked just right now, it's related to V naught. However, if we consider that V naught is due to third harmonic voltage, and this third harmonic voltage is independent of speed of our reference frame, and that is very obvious, because when you are talking about third harmonic, I have given you a very simple and crude explanation, like third harmonic is just like a something that is perpendicular to the uh, reference plane. Huh? Means rotating reference plane. So here, when you are having that third harmonic that is perpendicular to your rotating reference plane, and better to say that the third harmonic axis is just passing through the center of your reference frame, then whether the reference frame is rotating at 3000 rpm, 1500 rpm, uh, 600 rpm, it doesn't matter. If you place a, means even for a very high speed rotating disc, if you place or ask someone to stand at the center point, then he or she will not able to realize any such, means rotational speed of that disc. So same thing happens for third harmonic case, and that is why the third harmonic voltage is not able to get any contribution due to the speed of this rotating reference frame, and that is why it is always zero irrespective of the speed of your rotating reference frame. We call this as speed EMA because it depends on the speed of your rotating reference frame. If you increase the rotating reference frame speed, then obviously the corresponding contribution of your lambda q and lambda d on VQ and lambda q on VD will increase. One more thing you must notice that this VQ is dependent, this PDMF is dependent on your lambda d, and your VD is dependent on lambda q. So, what is the rationale behind this? See, that is very obvious that when we are talking about means uh, say if you consider a DC machine, what is the means voltage at, means will get at interpolar axis and at polar axis. If you can recall that, then you will get the answer that here, until unless it is 90 degree, this PDM must be 90 degree with your means voltage axis. So if we shift ourselves from 90 degree of our q axis, we will reach to d axis, and that is why you will observe this vq is dependent on your lambda d. It is omega lambda d that is going to contribute or going to alter the value of vq. And also in case of vd, it is minus omega r lambda q. Now, again, another interesting question, that why in case of VQ it is plus omega r lambda d, and in case of VD why it is minus omega r lambda q. You must think, and I expect at least one or two will ask me this question and will get back to me for um, the answer. Now, coming to the third part, this one, this one, this is our actually this is like a transformer EMF. Here you can see that it depends, like an transformer secondary induced EMF, it directly depends on the rate of change of your magnetic flux linkage. If we speed, that means ddt, if you apply a constant flux, then this will give you zero. And if you increase this flux linkage rate of change, you are going to get a higher contribution from them. However, here if we analyze, we will see that there is a definite contribution for V naught also, right? So this is our circuit. Okay, so mm, now let us do some mathematical manipulation. Here we can write this lambda qd0 is like, if we take only this lambda qd0, um, we can uh, means actually I made a mistake here. Here I must write that it is one IQ D0 must be multiplied over here. I just missed that term. Here I should write it should be means the whole thing. This whole thing should be multiplied by uh, IQ D0. Right. Now, if we, however, if we do simplification, what we'll get this lambda q is the first element of our lambda q d0 vector. We'll get that this is depending on LLS plus 3 by 2 L naught minus LMS. Now, what is LLS and what is LMS? I'll explain later. But this L naught, uh, can you recall that at the very beginning we were having two terms? One was A, another one was B. One A was associated with cos sorry, A was a constant term, but B, although being a constant term, it was associated with some cos 2 theta r. But here you can see that this 3 by 2 L naught minus LMS IQ. That means what I'm trying to say, if you see the equation of lambda q, lambda d, and lambda naught, in comparison with lambda A, lambda B, lambda C, we will understand that this expression of lambda Q is independent of your state rotor angular position, and that is what we were expecting or what we were looking for. Because if you cannot make your lambda, all these terms, independent of theta, then what will happen when you will do this kind of uh, you will try to find out the rate of change of flux linkage, then you will be in deep trouble, because every time you will get some kind of omega r term, because eventually you have to evaluate lambda, the flux linkage that is dependent on your theta, and this theta will being a time varying quantity will also give you some constant value of d theta dt. It's very annoying. And another thing that is very important to note here, that you to means let me one simple thing, that why we are interested for obtaining a mathematical model for synchronous machine. It is very obvious. See that in case of synchronous machine or in any machine, suppose if you have 100 megawatt or 1000 megawatt machine, you can have a very large machine. But means how that machine is going to behave, or how means even if you have received order from your uh, your buyer, or your, suppose you are working in a manufacturing plant and you have received an order. Now if you want to see that how your machine is going to behave, whether the machine will perform satisfactorily or it will not be able to fulfill your means objective or performance requirement, then what you should do, or traditionally what people used to do, they go for trial and run. They develop a machine, then but it was not economical. It involves a lot of money, it involves a lot of effort. You have to design a prototype, then you have to try, you have to test it several times to reach a definite conclusion. But nowadays what we do after innovation of computer, we develop a simulation model for our system. So we, instead of developing a physical circuit, like suppose if I ask you to study the current variation in an RL series circuit due to uh, typical voltage waveform, then you don't have to, even if I specify you the value of R and L, you don't need to rush to the market and buy the exact component Rather, you can always have MATLAB, PSpice, PSCAD, it app, all these kind of a lot of simulation software where you will easily find all these component by just a click of, means a mouse click. You can adjust their parameter, you can configure them, means you can have RL series circuit, RL parallel circuit, and you can simulate, and within a few minutes, if you are used to with those technology, you will be able to means study the response you are going to get from that kind of physical system. So that is the essence of developing this mathematical model and all this. But there is another issue is associated with all this mathematical model. That mathematical model, if it is a very vast one, because the time we are talking about this transformation, when Park developed this transformation or all this, it's 1920 to 1930. So when computer comes in the picture, means came in the picture in some after 1960 or 70, I am not good at history, you can check. But at that time also, computational ability was very primitive, means we were having means even during my young age, I have seen that we are having like I4 is when I was a student, just second year or third year student. I have also observed a lot of occurrences where we used to face that we used to uh, tag it like the computer is getting hanged. That means that the computer is running out of computational resources. Now we are having with this means tremendous improvement in solid state technology. We are having a huge means computational resources we can have, and we can compute anything. But that doesn't give us a blanket permission to waste our computational resources, like consume a huge volume of our memory space or consume RAM. So why I am saying all this to you, because if you see this expression here, if we have means theta dependent terms, then at every instant, means your computational means computation, say at a second, means depending on your clock frequency, will have number of computation performed by your computer. So now, for every different value of theta r, it will calculate d theta dt, d theta dt, and that will create a lot of burden, or it will result in a lot of computational wastage. So that is why it is very important to transform it and have a very simplified model like this. See, now this lambda q, lambda d, and lambda naught, they are independent of rotor mechanical position, and that is our first achievement. Now, see here that lambda f, uh, lambda f, lambda g, lambda kd, and lambda kq. We are having this from our expression. We can find out the expression of means we leave this lambda matrix intact. We do not alter the entries of lambda matrix, like here, as I have mentioned, that we are not ready to change the rotor equation, because the rotor term, if you can see here somewhere, it must be, yes, just a minute. Yes, these rotor terms were already, this LRR matrix was already independent of theta. So the rotor flux linkage will obviously only dependent on the rotor, means corresponding current variable. Here, as we can see that this, all this expression, this lambda a, this doesn't depend on rotor position. Similarly, lambda kd, lambda g, lambda kq, all these doesn't depend on the rotor position. Interestingly, another thing we must note that lambda, if there is no q axis winding current, like no iq, no ig, if we consider this, I'm talking about this lambda if we see that there is no iq, no ig, no ikq, and if we consider this lambda g, then similarly there is no id, no if, no ik right? So here we can see that this here also it should be like I have made a mistake here, a correction. This should be ikq, means that the index of this individual inductor are very simple. The current responsible and the winding you are considering. Like here we are considering, um, say, if we see this one, this lambda, sorry, lambda g, lg. LGG means you are considering the first G indicates you are considering the flux linkage of G winding, and the second G indicates it is due to G current, means G winding current. Similarly, this lambda G LGKQ, it indicates you are considering the corresponding flux linkage of G winding, that is lambda G, and it is this LGKQ indicates it is due to the current KQ. So here it should be IKQ. It should be IKQ. Right. Now, all these are more or less okay. So let us move in that next one. Here, please note this matrix. Right. This is a very interesting matrix. Here you can see